In noisy physical systems, like analog circuits, quantum devices, or even biological neural networks, computation is never perfectly deterministic. There's always noise, fluctuation, and randomness. And yet, these systems still manage to perform complex tasks. How? The key lies not just in how they process input signals, but in how they transform noise, not as a flaw, but as a feature. This is the story of innovation capacity, a new way to understand the true computational power of physical reservoirs. Let's begin with a paradox. In reservoir computing, we often measure a quantity called information processing capacity, or C/text IP. It tells us how well a linear readout can predict tasks based on the input history. But in real noisy systems, C/text IP can be far smaller than the rank of the readout covariance, the total number of independent dimensions in the system's output. So where does the missing capacity go? It doesn't vanish. It's reallocated, not to predicting inputs but to something deeper, innovation. In classical signal processing, the DUB innovation refers to the part of a process that cannot be predicted from past inputs. It's the fresh, unpredictable information, driven by noise, mixing with signals, and generating new structure. In a noisy reservoir, this innovation isn't just noise, it's computation. We define innovation capacity, CI, as the total capacity allocated to tasks orthogonal to the input filtration. Essentially, the system's ability to generate novel, distinguishable output patterns from intrinsic randomness. And here's the breakthrough, a conservation law. C/text IP plus CI equals \text rank \sigma Roman 20 \lect D. The total observable rank of the readout covariance splits exactly into predictable and innovation components. Whatever C/text IP loses in noisy settings, CI gains. The system doesn't lose capacity, it redeploys it. Now let's see this in action. Take a simple RLC circuit, resistor, inductor, capacitor, driven by a signal and thermal noise. In steady state, its output covariance decomposes as \sigma Roman 20 T equals S plus Tn0, where S$ is the signal-driven component, and Tn0 is the noise-induced innovation, scaling linearly with temperature. This leads to a beautiful temperature trade-off. As temperature increases, C/text IP decreases monotonically, while CI increases, always preserving their sum. You're not losing computational power, you're shifting it from prediction to exploration. But this isn't just a linear story. Consider a nonlinear Duffing oscillator, used in many physical reservoirs, driven near a carrier frequency, read out in baseband IQ. After demodulation and slow envelope approximation, the system's dynamics become tractable. Here, the predictable response comes from linear and cubic deterministic terms. But the innovation, it's not just noise, it's the demodulated thermal fluctuations, scaled by \sqrtt, and crucially, nonlinearly mixed with the signal. Even at low temperature, this mixing generates additional covariance beyond the linear noise term. So we model the total covariance as \sigma Roman 20 T \beta \approx S \beta plus Tn1 \beta plus \beta 3 GT \beta bar N \beta I2, where \beta is the nonlinearity strength, GT, \beta captures higher order mixing, and bar N is an isotropic inflation term. Simulations confirm this model. As \beta and T increase, CI grows significantly, especially in the mixed signal noise sectors, showing that innovation is not just noise but a structured computational resource. Now, what does this mean geometrically? Let's work in whitened coordinates. Transform the readout so that its covariance becomes identity on the active subspace. Then, the predictable and innovation components become complementary ellipsoids. The predictable part has semi-axes \sqrt \gamma k, and the innovation part \sqrt1 \gamma k, where \gamma k are the eigenvalues of the predictable fraction operator. And here's the insight. CI is the trace of the innovation fraction operator. So CI is literally the total whitened innovation volume budget. A large CI forces a high-dimensional innovation subspace, meaning many independent directions in which the system can generate unpredictable, distinguishable behavior. Now here, is where it gets profound. Under mild regularity assumptions, a large CI implies extensive block differential entropy. Specifically, fix a block length B$ and define the \tau innovation subspace, those directions where the innovation fraction exceeds \tau. Let L\tau be its dimension. Then the projected innovation block Y, BT, has a one-step covariance floor. \text cov Y BT \succec \tau/2 IM, where M equals L\tau B. This isn't just noise. It's structured, high-dimensional randomness. And by the asymptotic equipartition property, the entropy of such blocks grows linearly with M. So the number of distinguishable histories grows exponentially. \text number of distinguishable histories, \sim x left, H, Y, B, T \right. With H, Y, B, T \gtr sim frac m2 log left, frac tau2 L *2 right, where L $$ is a bounded isotropic constant. In other words, a large innovation budget means exponentially many distinguishable output histories, even if the system is deterministic in its dynamics. This is not just theory. It has a concrete consequence. Learning the innovation law is hard. We prove a total variation learning lower bound. To estimate the innovation block distribution within total variation distance \alpha, you need at least n equals \omega, m/\alpha 2, samples, where m equals L/tau b is the effective innovation dimension. This is formal evidence of generative utility. Physical stochastic reservoirs aren't just for prediction. They're capable of generating complex, diverse, and information-rich output sequences, making them powerful tools for generative modeling, memory, and even quantum-inspired computation. And this all stems from a single, elegant principle. In noisy dynamical systems, computation isn't just about inputs. It's about how the system transforms noise into structured innovation. So the next time you see a noisy physical system performing a task, whether it's a circuit, a network of oscillators, or a quantum device, don't just ask, what's it predicting? Ask, what is it innovating? Because in the end, the most powerful computation may not be in the signal, but in the noise.